August 2020, California. The control room at the California Independent System Operator hummed with tension as engineers stared at screens flashing red. Demand was climbing past 47,000 megawatts, shattering records set just days before. Outside, the thermometer read 115 degrees Fahrenheit in Sacramento, 118 in Fresno. Inside homes across the Central Valley, families watched their air conditioners labor against heat that turned living rooms into ovens. The grid was failing, not all at once, but in carefully managed waves of darkness as operators made impossible choices about which neighborhoods would lose power next. Hospitals switched to backup generators with fuel tanks that weren't meant to run for days. Elderly care facilities checked and rechecked their oxygen concentrators, knowing that another rotating blackout could mean life or death for residents whose bodies couldn't regulate temperature anymore. In one facility outside Modesto, the coordinator moved between rooms where temperatures had climbed to 92 degrees despite every window open and every available fan running. Her breath came short in the stifling air as she checked on a woman in her 80s, skin paper-thin and dry. The backup generator rumbled outside, burning through diesel at a rate that left maybe 6 hours before the tank ran empty. Maybe less. Back at the ISO control room, the math was brutal and simple. Natural gas plants were maxed out, their turbines screaming at full capacity. Solar arrays that had carried the afternoon load were dropping off as evening approached, exactly when demand spiked as people returned home. Wind farms in the Altamont Pass sat mostly still in dead air. Battery storage systems, still sparse across the state, drained within hours. The deficit kept growing. 3,000 megawatts, enough to power 2 million homes, just gone from the grid with no clear way to replace it. This wasn't California's first energy crisis. The blackouts of 2000 and 2001 had scarred the state's memory, but this time felt different. Climate change wasn't a future threat anymore, but a present reality, each heat wave more intense than the last. The infrastructure built for a cooler California couldn't handle what the state had become. Grid operators needed mobile power, and they needed it immediately. Diesel generators were too small, scattered across the state in insufficient numbers. Mobile gas turbines existed but took days to transport and connect. Days that people in care facilities and hospital wards didn't have. The state was running out of options as the sun set on another triple-digit day. But somewhere in Wyoming, sitting on heritage rails in Cheyenne, a machine built in 1941 held an answer no one had considered. Not a generator, not a turbine, a locomotive. The largest steam locomotive ever built, restored and operational, capable of something most people had never imagined. What if the solution wasn't in the future, but preserved from the past? Union. Pacific 4014 stands 132 feet long and weighs 1.2 million pounds. Restored to operation in 2019 after 6 decades of retirement, it represents the pinnacle of steam locomotive engineering. 25 driving wheels, each 7 feet tall. A boiler that holds 23,000 gallons of water. A firebox that burns oil at temperatures exceeding 2,000 degrees Fahrenheit. The big boy was built to haul freight over the Wasatch Mountains, designed to move 6,000 tons of cargo where other locomotives strained and failed. But most people who watch it roll past on heritage runs miss what it actually is. A steam locomotive isn't just a machine that moves, it's a mobile power plant on rails. The firebox heats water in the boiler, creating steam at pressures exceeding 300 pounds per square inch. That superheated steam, contained and controlled, represents enormous thermal energy. In normal operation, it drives massive pistons that turn the driving wheels, but the same steam that creates motion can drive turbines, and turbines can generate electricity. The physics are straightforward: heat water, create high-pressure steam, channel that steam through a turbine generator, and produce electrical power. The big boy's boiler, operating at full capacity, generates thermal output comparable to a small natural gas power plant. Estimates put its potential electrical generation, with proper turbine coupling, between 2 and 5 megawatts. That's enough to power 2,000 to 5,000 homes or several critical facilities operating simultaneously. This isn't theoretical engineering. During World War II, locomotives served as emergency power sources when local grids failed or didn't exist. Post-war industrial operations used steam engines to power sawmills and factories during outages. The precedent existed, scattered through railway history in moments most people never learned about. In 1998, a diesel-electric locomotive powered municipal buildings in Boucherville, Quebec, during an ice storm, running for days as an improvised generator. But steam presents different challenges and different possibilities. The engineering barriers are real. Modern electrical grids require precise 60 Hz alternating current. Voltage must be regulated to match distribution standards, typically between 12 and 15 kilovolts. Phase synchronization matters because injecting power into an existing grid without matching its frequency and phase can destabilize the entire system. And the big boy, for all its massive capability, was never designed to maintain the kind of steady, sustained output that grid interconnection demands. But what was impossible in 1941 becomes achievable in 2020. Modern inverter technology can take variable mechanical input and produce clean, grid-compatible electricity. Steam pressure can be regulated with precision that early engineers never imagined. Computer monitoring can track every variable in real time, adjusting fuel flow and steam release to maintain stable output. The big boy isn't obsolete. It's a bridge between eras, century-old thermal engineering meeting 21st century electrical control. Yet knowing something is theoretically possible and actually doing it are separated by risk, bureaucracy, and one crucial phone call. The California Energy Commission met virtually on a Friday afternoon in August, screens filled with tired faces searching for answers that didn't exist. Every conventional option had been discussed and dismissed. Mobile generators were too small or already deployed. Gas turbines would take 3 days to transport and connect. 3 days that hospitals and care facilities didn't have. Someone mentioned Union Pacific's heritage fleet, almost as a joke. Steam locomotives as power plants. The room went quiet as engineers started doing math on notepads and laptop screens. The call to Union Pacific's heritage operations manager came an hour later. The request sounded absurd at first. Could the big boy serve as an emergency power source for critical facilities in Sacramento? The manager's initial reaction was protective. This wasn't just any locomotive. It was an $8 million restoration, irreplaceable, the crown jewel of Union Pacific's historic collection. But the urgency in the caller's voice was impossible to ignore. People were at risk. The state was desperate. Within 2 hours, the question reached Union Pacific's corporate leadership. Risk assessments began immediately. Financial risk topped the list because potential damage to the big boy could run into millions. Operational risk followed since pulling the locomotive from scheduled heritage appearances meant disappointed crowds and broken commitments. Legal liability loomed large. If something failed, if the connection destabilized the grid or damaged the machine, who would be responsible? Insurance companies were called. Lawyers reviewed contracts. But the engineers saw something else. They saw an opportunity to prove that heritage assets weren't just museum pieces rolling on weekend excursions. They saw a chance to demonstrate that old technology, properly applied, could solve modern problems. The chief mechanical officer made the case directly. The big boy was built tough. It had survived decades of heavy freight service, then 60 years of retirement, then a complete restoration. It could handle this. The decision came Sunday morning. Union Pacific would do it with conditions: real-time monitoring of every system, immediate shutdown protocols if stress indicators appeared anywhere, complete post-operation inspection before the locomotive returned to any other service. California's governor issued emergency authorization. Insurance was settled through the state's disaster fund. The timeline was set at 72 hours from approval to operation. Teams assembled rapidly. Union Pacific's steam shop crew in Cheyenne prepared for departure. Electrical engineers specializing in grid. Connections flew to Sacramento. A mobile steam turbine generator, normally used for industrial applications, was located and trucked toward the chosen site. Sacramento Rail Yard was selected for its direct mainline access and proximity to hospital districts that needed power most desperately. Water supply lines were mapped. Fuel trucks were positioned along the route from Wyoming. The big boy's engineer stood in the Cheyenne shop as the locomotive was fired up for departure. Steam began to rise from the stack, pressure building in the massive boiler. This wasn't a heritage run with families waving from grade crossings. This was a mission. Lives depended on what happened next. The big boy rolled out of Cheyenne on Sunday evening, black smoke trailing against a darkening Wyoming sky. This wasn't the careful, ceremonial pace of a heritage excursion. The crew pushed harder, moving with urgency while monitoring every gauge and bearing temperature. 900 miles separated Wyoming from Sacramento, and the clock was counting down for hospitals running on generators that weren't meant to sustain operations for days. Across the high desert of Wyoming and into Utah, the locomotive thundered along freight lines that had carried countless trains but never one on a mission quite like this. The crew rotated in shifts, maintaining constant communication with Union Pacific Dispatch. Boiler pressure held steady at 300 pounds per square inch. Bearing temperatures stayed within normal ranges. Oil consumption tracked according to predictions. Every detail was logged because this machine had to arrive ready to work immediately, with no time for repairs or adjustments. Rail fans tracking the big boy's progress online began gathering at grade crossings, cameras ready. Social media erupted with speculation and excitement. News helicopters picked up the story as the locomotive crossed into Nevada, following the path of the historic Transcontinental Railroad. The visual was striking in a way that modern railroading never provided. A steam plume visible for miles, a machine from 1941 racing to solve a crisis in 2020. Some saw it as spectacle. Others saw desperation. Both were right. Union Pacific's mechanical team monitored telemetry remotely from Cheyenne, watching data streams from sensors placed throughout the locomotive during restoration. Any anomaly in bearing temperature or pressure regulation would trigger an immediate slowdown. Water stops were coordinated with precision at designated points along the route. Fuel trucks waited at scheduled intervals. The mathematics of the journey were unforgiving. Fuel consumption versus power delivery versus time until the next wave of blackouts. There was no margin for error or delay. The big boy crossed into California as the sun set Monday evening, climbing through the Sierra Nevada and descending into the Sacramento Valley. The temperature still read 105 degrees Fahrenheit at 8 o'clock. Radio traffic from the California ISO reported another round of rotating blackouts beginning within hours. The hospital coordinator in Modesto checked her backup generator's fuel gauge. 4 hours of capacity remained, maybe less if the heat persisted. Sacramento Rail Yard came into view just after midnight. Work lights illuminated the designated area where electrical crews had already staged equipment. The mobile turbine generator sat positioned and ready. Fire suppression equipment stood by. Hospital administrators watched from a safe distance, their facilities' backup systems burning fuel with every passing minute. Media crews waited behind barriers, cameras ready but kept at a distance for safety. The big boy reversed carefully onto the designated siding, engineer and conductor working with ground crew using laser alignment tools. Century-old technology meeting modern precision. Every connection point mattered. The water tender was positioned for continuous feed. Fuel trucks stood ready for around-the-clock refueling. The moment had finally arrived. Steam lines were coupled from the big boy's dome to the turbine generator in the pre-dawn darkness, each connection checked and rechecked by engineers working under portable lights. Heavy electrical cables ran from the turbine output to a mobile transformer, then 500 feet to the grid interconnection point. California ISO observers approved each step, verifying safety interlocks that would trigger automatic shutdown if frequency drifted or pressure spiked beyond safe limits. The big boy's firebox was stoked to full operational pressure, the steam dome gauge climbing steadily toward 300 pounds per square inch. At 3 a.m, the first steam was released to the turbine. The generator spun up with a rising hum that cut through the night air. Electrical engineers watched oscilloscopes intently monitoring frequency. 60 hertz, holding steady within tolerance. Voltage regulation showed stable at 12.5 kilovolts. Grid synchronization protocols began, waiting for final clearance from the ISO control room. Thermal imaging cameras scanned every connection point, searching for hotspots that might indicate problems. Vibration sensors on the turbine bearings reported readings within normal limits. The big boy's crew monitored boiler pressure, water level, and combustion intensity. On the electrical side, engineers watched their instruments like surgeons in an operating room. The hospital coordinator's voice crackled over the radio. Her facility was down to 2 hours of backup generator fuel. Everything was ready. One switch remained, the grid interconnection breaker that would send the big boy's power into California's electrical system. The ISO engineer's hand rested on the control, waiting for the final clearance that came at 3:17 in the morning. The breaker closed with an audible clunk that echoed across the rail yard. Ammeter needles swung sharply. 2.3 megawatts flowed from a 1941 steam locomotive into a 21st century power grid. The hospital administrator watching his facility's power monitoring panel saw the reading stabilize immediately. Lights that had been running on backup power now drew from the grid, fed by steam and fire and engineering that predated his own birth. The backup generators spooled down, their fuel crisis averted. In the care facility outside Modesto, the coordinator felt cool air finally beginning to flow from vents as the air conditioning system, no longer rationed to preserve generator fuel, returned to full operation. But this wasn't a test run that could end after an hour. Weather forecasts predicted the heat wave would persist for another 4 days minimum. The state's conventional power sources remained insufficient during peak evening demand. The big boy had just become a critical node in California's electrical grid, and it needed to keep running. Water consumption ran at more than 1,000 gallons per hour under operational load. A dedicated water truck rotation began immediately, supplemented by an emergency authorized hookup to fire hydrants. Fuel trucks pumped oil directly into the tender, maintaining supply for combustion that consumed 180 gallons every hour. The big boy's crew settled into 8-hour shifts, 3 teams rotating through continuous operation. This was no longer a heritage operation or an emergency response. It was sustained industrial service. The big boy ran for 96 hours straight, feeding power into California's grid while temperatures remained above 100 degrees. When the California ISO finally announced that new capacity was coming online and grid stress was easing, the locomotive had delivered approximately 220 megawatt-hours of electricity, enough to power more than 2,000 homes for 4 days, or to keep 3 hospitals, 2 elderly care centers, and an emergency services hub operational through a crisis that could have claimed lives measured in dozens or more. Union Pacific's master mechanic arrived from Cheyenne before the big boy's boiler had fully cooled. The inspection that followed was exhaustive and anxious. Every bearing was examined. Every boiler tube was tested with ultrasound equipment, searching for stress fractures or metal fatigue that could indicate permanent damage. The running gear, drivers, connecting rods, and journals all received scrutiny that went beyond routine maintenance checks. The question everyone needed answered was whether saving lives had cost an irreplaceable piece of history. The verdict came after 3 days of assessment. Minor wear consistent with 400 miles of travel plus sustained stationary operation. 1 boiler tube needed resealing, expected maintenance for any steam locomotive after heavy use. Bearings measured within acceptable tolerances. The firebox refractory required minor patching. Total repair cost ran approximately $45,000, far less than the worst-case scenarios that had kept Union Pacific's leadership awake at night. The big boy had survived intact. The financial accounting told an unexpected story. Fuel, water, crew overtime, equipment rental, and repairs totaled roughly $180,000 for 4 days of operation. A mobile gas turbine rental would have cost $50,000 per day, reaching $200,000 for the same period. More importantly, the gas turbine would have required 48 additional hours to transport and connect, time that the hospitals didn't have. The big boy wasn't just symbolic. It was cost competitive and faster to deploy than conventional alternatives. Media coverage spread internationally. Engineering journals analyzed the feasibility and questioned whether this approach could be replicated elsewhere. Heritage preservation communities found themselves divided between celebrating the resourcefulness and worrying about the risk to irreplaceable artifacts. Union Pacific received goodwill that no advertising budget could purchase. The big boy's fame elevated from railfan icon to proven infrastructure asset. But the operation raised questions that extended far beyond 1 locomotive in 1 crisis. California's grid vulnerabilities were exposed in ways that couldn't be ignored. The pattern repeated across North America. Texas froze in 2021 and its grid collapsed. Europe brought retired coal plants back online during energy shortages in 2022. When modern systems fail, communities reach for whatever works, even if it means pulling solutions from the past. The Big Boy returned to Heritage Service after repairs, but with modifications. Permanent mounting points were added for turbine generator coupling. If needed again, the locomotive could answer another call. Grid modernization costs are estimated at more than $2 trillion over 20 years, and the gap between needed investment and actual spending continues to widen. More crises are coming. When the grid fails again, and it will, where will we turn? Sometimes the answer isn't building something new, but remembering what we already built and why it still matters. I'd love to hear your thoughts. Please leave a comment below and give this video a like if you enjoyed it. See you on the next one.